Okay, so let's resume our discussion on buckling. Okay, so so far we have discussed buckling in rigid bodies, 1 degree of freedom system, 2 degree of freedom system, and then in last class buckling in beams. So a beam has infinite degree of freedom, so we had infinite solutions, right, to the algebraic equations. So now we will look at the problem of buckling in beams with energy methods, right? So we saw that the problem of buckling in beams using Newton's method was a long process to derive the equations, and then it was even longer to solve those equations, right? So we are now going to look at buckling in beams using energy methods. Okay, but first let's revisit the governing equation for a beam under axial loads. So the governing equation that we derived in last class, it's a fourth order differential equation. Did I write EI or H33 in the last class? Okay, so I'll write now H33. Okay, for beam in bending. Okay, and then I have transverse displacement U2, right? Then what was the next term? Just that? So the contribution of axial force will enter the differential equation with the second order derivative with respect to the transverse deflection, okay, is equal to P2 if present. If there is a transverse distributed load applied, P2, which varies with respect to x1, for example, then we will have this equation, right? So we saw a derivation of this equation and the respective boundary conditions in the last class using Newton's method, right? So today we are going to look at a derivation of this equation using energy methods, not in too much detail, but so that you get an overview of how it's done, and then we will solve a problem using energy methods. Okay, so recall that the work done by internal forces is equal to negative of the strain energy, which is equal to integration 0 to L n1 epsilon 1 plus m2 kappa 2 plus m3 kappa 3 dx1. So here n1 is the axial load, m2 is moment about I2, and m3 is moment about I3. Okay, so we have used this equation before while applying unit load method, right? And if you look at the slides which have already been posted as energy methods, you can find a derivation here on how to get the internal work done in terms of the moments and curvatures. And similarly for a twisting beam, for a 3D Euler-Bernoulli beam. Okay, so let's quickly go over this derivation. An infinitesimal element is subjected to moment m3, so there will be an angular displacement of phi3 on this face, and Taylor series expansion on the other side will result in phi3 plus d phi3 over dx1 times dx1, right? and then we are just summing that over the element, because that's the work done. Moment times the displacement is the work done. So moment times the work done on the left face, on the right face, summed up for the total element. Okay, so when you do that, you will get this expression, and this is integrated for the entire beam's length, because this is for the infinitesimal element, right? So when you integrate it for the entire beam element, you get the internal work done is equal to integration of dW, which was for the small element, and then you get this expression, right? So this is for only M3. You can do this for M2 when a moment about I2 is applied. You can do it about twisting moment, and you can do it with the axial force. So you will get a general expression for a beam in bending like this, right? We already used it in unit load method. And we also know that the total potential is A plus phi, where this is the internal energy, and this is potential due to externally applied loads. Okay, so the total potential is internal energy plus the potential due to externally applied loads. We used this to derive total potential expressions for the 1D beam, for the rigid bar, 1 degree of freedom systems, 2 degree of freedom systems, and so on. So we will use the same thing. It's just that internal energy in this case would be derived using the work done instead of the spring potential that we used to have as the internal energy in the rigid bar systems. So if the bar is rigid, the only internal energy that we have is due to the springs, but if the bar is flexible, we would have energy due to the beam's strain energy, right? The beam's internal energy. So let's say we have a beam, okay, and there is a distributed load applied on the beam, and this is I1 and this is I2. So the distributed load is applied along minus I2, and that's P2 x1, okay, and the beam is of length L, subjected to axial loads N1. So there are both axial and transverse distributed loads in the beam. The beam is of length L, and now we will populate our expression for the total potential. So that becomes 1/2 integration 0 to L H33C d square U2 over dx1 squared whole square for the differential dx1. Okay. So moment expression can be written in terms of curvatures. So that will become H33 kappa 3, and then kappa 3 is replaced with the expression, the strain displacement relation, right? The other way to obtain this expression is through the volumetric energy. So the volumetric energy is sigma times epsilon. It's half integration 0 to L, integration over the volume, sigma transpose times epsilon dV. So you can either use this expression, this is energy, and then you can use your constitutive equations and your strain displacement relations to obtain this expression. So you need to know either one of these methods.
So that's what bottom I equals the total potential also equals that. You can also get it by doing that.
Yeah.
Okay. Thank you.
So you have to use constitutive equation, sigma is equal to E epsilon or nonlinear constitutive, and then you have to use strain displacement relation, right, which we have derived for Euler-Bernoulli beam theory, and then you get this expression. Okay, now the external potential, the potential due to externally applied loads. So we have two loads, one is N1 and one is P2x1, right? N1 is the axially applied load, P2x1 is a distributed load. So due to P2, the potential is integration 0 to L because it's a distributed load, P2x1 times U2 bar x1 dx1.
Wait, so is it A equals that? Is it still pi or is it A? Because that's the internal.
Oh yeah. So this is A. Yeah. I started populating pi, but ran out of space on the board. So yeah, this is internal energy, and we will substitute this expression in the expression for total potential. So the potential due to the externally applied load is P2 times U2 is the potential, right? But that's a distributed load, so we have to integrate over the length. So integration 0 to L P2 x1 times U2 x1, and there is a negative sign because P2 is in the direction of minus I2, right? Okay, and then we have a component due to N1, so that will become minus N1 delta. But N1 is applied along positive I1, so it will be plus N1 delta. Okay, so what's delta? Let's take an infinitesimal element again in the beam. Okay, so if we take an infinitesimal element of length, let's say dx1, and there is N1 applied on both ends, and this element is being deformed such that there is a transverse displacement, right? So the work done by this force N1 is going to be the force times displacement, and that displacement will be this component of the total displacement, right, delta. Okay, and it's an Euler-Bernoulli beam theory, so this angle is du2 over dx1, the slope. So delta can be written as dx1 minus this length is dx1, so dx1 times cosine of that angle, cosine du2 over dx1. Any questions at this point? So what I'm trying to find is this delta, which is dx1 minus a component, a cosine component of this dx1, right, and that's cosine of du2 over dx1, and then I will expand this expression using the trigonometric series, so it becomes dx1 minus dx1 times 1 minus 1/2 du2 over dx1 whole square plus higher order terms. So this is an expansion for cosine, right? So I will neglect all the higher order terms, the cubic or fourth order terms, whichever they are. So simplifying this expression becomes dx1 minus dx1 plus 1 half du2 over dx1 whole square, the square of the term, times dx1. So this will cancel each other and delta is left with that expression 1 half du2 over dx1 whole square dx1. Any questions? Okay, so let's rewrite the expression for the potential due to externally applied loads. Phi will become 1 half integration 0 to L n1 x1 times du2 over dx1 whole square dx1, right? And then we have the other term, which is minus integration 0 to L p2 x1 times u2 bar x1 dx1. So now we can write our total potential, which is 1 half integration 0 to L h33c second order derivative of u2 with respect to x1 and the square of that term times dx1 plus 1 half integration 0 to L n1 times du2 over dx1 squared dx1 minus integration 0 to L p2 x1 u2 bar x1 dx1. Let me just write u2 times dx1, assuming u2 is a function of x1 in the entire expression. Okay, so this is the expression for the total potential. We have the component of strain energy and the energy due to externally applied loads, right? So to find the governing equations or the equilibrium equations, what do? We say that the variation of potential is equal to 0, right, for equilibrium. And then we take the variation of this expression. So that becomes one half of integration 0 to L h33c 2 times second order derivative of u2 with respect to x1, then times variation of the second order derivative of u2 with respect to x1. Does this make sense? It's like chain rule for differentiation, but here we are doing a variation. Okay, so it had a square, so the 2 comes in front, then you write the expression and then you take the variation of the expression. Okay, and then you have the second term, which is 1 half integration 0 to L n1 times 2 times the derivative of u2 with respect to x1, then you will take a variation of u2 with respect to x1, right? And then you have the third term, which is integration 0 to L p2 x1 times variation of u2 with, and then integration with dx1, because there is no squared term here, so I just took the variation of u2. Can I erase this portion? Okay. So all this information is also present in the slides. Whatever we discussed, the calculation of this delta, so that we can find the work done, and then we got the externally applied the potential due to externally applied load. Then we calculated the total expression for the total potential and took the variation. So far we are at that stage, and now what we are essentially doing is taking the derivatives of from the terms which are associated with variation. Okay, so for example, this term, it can be written as second order differential with respect to variation in u2, and then differential with respect to x1 square, right? Because the variation operators and the differential operators are interchangeable, like the differential operators. So if you had two variables like x and y, you differentiate first with x and then with y, or do vice versa, it doesn't matter, right? So same thing goes with variation. You can just use them in any order. So you can write this expression or this term by changing or swapping the order of the variation differential, and you know that this quantity is an arbitrary quantity, the variation in u2, but you cannot say anything about this quantity, right? So you would do integration by parts on this term twice, so that you can shift the differentiation from this term on the other term, right? So the integration by parts is, let's say there are two terms, you integrate the first one, or you differentiate the first one and then you integrate the second one, right? So you will integrate this term and you will differentiate this term. So you are essentially shifting the derivatives from this term to this term. Any questions? So we swap the order of variation and differentials, and then we integrate by parts twice on this term because we have second order derivative, but for this term we have first order derivative, so we will integrate this term by parts only once, right? So when we do that, we get this expression. So you can see that in this expression we have I think there is an error here. So let me write down this term again. So it will become integration 0 to L variation in u2, and then second order differential with respect to x1 h33c, second order derivative in u2 with respect to x1, minus d over dx1 n1 du2 over dx1 minus p2, and integration with respect to dx1. So this entire term, oh actually yeah, that's present here. I was looking at some other term. So yeah, Uh, after integration by parts, we will get this term where we applied integration by parts, right? And then we will have two other terms which are definite integrals, which are a result of definite integrals, right? So those are h33 times second order derivative of u2 with respect to x1, and then delta du2 over dx1, and it's a definite integral 0 to L. And then we have another term which is n1 du2 over dx1 minus d over dx1 h33 second order derivative of u2 with respect to x1 times variation in u2, and again this is also a definite integral. So these two terms are a result of the integration by parts. So when you do integration by parts, you will get two terms. One is present here and the second is present here. Okay. So now let's look at this equation. Delta u2 is an arbitrary quantity. Okay. So if this entire expression has to go to 0 because variation of total potential is 0, delta u2, which is the variation in u2, cannot be 0, right? Because it's arbitrary. So its coefficient has to go to 0, right? And what does this coefficient look like? The governing differential equation, right? Fourth order differential of u2 with x1, second order differential of u2 with x1 with a force with an axial component, right? In our case, N1 is tensile. In this case, P was compressive. So that's why the change in sign. And then minus P2, which is the distributed load. So we get the governing differential equation for the beam cross section. What else do we get? Using energy methods, we get boundary conditions as well, right? For example, if this was a cantilever beam, right? So at x1 0, we have displacement 0 and the slope is 0, right? So its subsequent derivatives, the third order and the second order derivatives, will also be 0, right? So when you substitute 0 in these expressions, you will lose this term because it has a derivative of u2 with x1, and then you will lose this term because it has a derivative of u2 with x1 and they are zeros. When you substitute 0 in that expression, you will lose that term, right? So what you get is these expressions at L, which are your shear force and moment boundary conditions, right? So this one is going to be 0. So this entire term represents the moment. h33 second order derivative of u2 with x1, because this term is arbitrary. And then this term is your shear force boundary condition, right? It was the resultant shear force. We saw yesterday that the shear force boundary condition has another term due to the axial force. So using energy methods, we can get the shear force boundary condition, the moment boundary condition if it's a cantilever beam. But if this beam was a simply supported beam, we would get the moment boundary conditions and the displacement boundary conditions accordingly, right? So let's try and solve an example using energy methods. So far what we have done is used energy methods to derive the equilibrium equations. We used Newton's method in the last class to derive the equilibrium equations, the governing equations, right? So now let's take a beam, a cantilever beam, which is subjected to a compressive force P, and then there is a distributed load which is of the form of a sine function. So P2x1 in our expression there is equal to minus P0 sine pi x over L. Okay, so this is essentially applied downwards, right, with a negative sign. Okay, and now we can write our internal strain energy, which is 1/2 integration 0 to L H33 second order derivative of u2 with respect to x1 and square of that term times dx1, right? Any doubts about this? And we can also write the potential due to externally applied loads. So that is 0 to L P2 x1 times u2 x1 dx1 minus the axially applied load P times delta, right, the work done by externally applied load. Okay, so now the total potential becomes integration 0 to L 1/2 H33 second order derivative of u2 with respect to x1 squared minus P over 2 du2 over dx1 squared plus P2 x1 times u2 bar integration with dx1. Okay, so to apply energy methods, let's assume a solution. Let's assume a solution such that u2 bar is a constant c times sine pi x over L. Okay, so why do I assume a solution? There are two reasons. One, in the last class we saw that when we solve this problem we get an expression like this as the displacement, but that's not a very good reason. So this expression satisfies my geometric boundary conditions, right? When my x is 0, this expression is 0. My apologies, we are taking a simply supported beam in this equation. So we have a simply supported beam and we are applying a sine load on it. Okay, so the strain energy or the potential due to the externally applied loads doesn't change because that's the characteristic of the beam, and we are assuming a solution such that u2 is also a sine function, right? So this u2 satisfies the geometric boundary conditions that the displacement u2 is 0 when x is 0 and it is 0 when x is equal to L, right? So that's why we can assume such a solution, And now using energy methods, we will find a value of constant C that will minimize or at least satisfy the principle of stationary total potential energy, right. So principle of stationary total potential energy says that the variation of potential is 0. So in this case, we have the total potential expression as integration 0 to L 1/2 H33C minus C times sine pi x over L pi square over L square. So I substituted u in the previous expression for potential, and then after differentiation I get this expression minus p over 2. Then I will differentiate again, so c times cosine pi x over L times pi over L, and this is squared, there is square there, and then I have one more term which is minus p0 c sine pi x over L dx1. Okay, so I substituted the value for u2 and carried out all the differentiations which were in the expression for total potential. And now I will carry out the integrations. So after carrying out all the integrations with respect to x1, I get L over 4 c square pi square over L square H33C pi square over L square minus P minus 2 P0C. Okay, so this is the expression for total potential in terms of the constant C, which is unknown, right. Okay, so what can I do using the principle of stationary total potential energy? I can differentiate the total potential with C and equate it to 0, right, because it should go to 0 for equilibrium, and then we get that this differentiation is L over 4 2c pi square over L square times H33C pi square over L square minus P minus 2 P0. So I differentiated the potential with respect to C and we get this equation, and we set this equal to 0, right, because differentiation of total potential with C is equal to 0. So we can calculate C as P0 L raised to power 4 over pi square H33C pi squared minus PL square. Okay. So we have now got an expression for the displacement profile, right? U2 x1 was c times sine pi x over L, right? So U2 x1 is equal to P0 L raised to power 4 over pi squared H33C pi squared minus PL squared sine pi x over L. Okay, So what else do we want from this analysis? We want to find a critical load at which buckling happens, right? So what was the critical load for buckling in a simply supported beam? Pi squared EI over, right, for a simply supported beam. Right, and we have learned that if we have energy methods, or if we are using energy methods, then we can understand the character of the beam or characteristic deformation of the beam using the second order differential of the total potential, right? So let's study the second order derivative of total potential with respect to C. So that becomes L over 4 2 pi squared over L squared times H33C pi squared over L squared minus P, and this second order derivative with respect to C should be greater than 0 for stability, right? So if the second order derivative is greater than 0, the potential energy will be a minimum at that equilibrium solution, right? So if we want a minimum potential energy for stability, we want this term to be greater than 0. And for this term to be greater than 0, this expression has to be greater than 0, right? So H33C pi squared over L squared should be greater than P, right? So P critical is equal to H33C pi squared over L squared, and H33C is EI for homogeneous uniform beam. So using energy methods, we can derive the P critical. So another reason why we use energy methods is that there are a lot of methods which are based on approximate solutions, and they all are very good to be applied on the energy itself. Today we saw that we took one assumed solution which was more or less an exact solution. It was not an approximate solution, but even if it was an approximate solution, we could have found a very good result for the total displacement profile, right? So we just used an assumed solution which took the shape of the exact solution, found the constant using principle of stationary total potential energy, and then we calculated for the constant the unknown, and finally we used the principle of minimum total potential energy, right, to find the character of the system. We say that this, for stability, the second order derivative should be greater than 0 because the potential will be a minimum, and that will be a stable solution, a stable equilibrium solution. So the condition is such that the P, the load, should be less than this load for stability, and that's our critical load. Any questions?
If we don't assume V2 equals C prime,
Yeah.
is there no way to solve the problem?
I think you need to know the displacement profile. So what you would do is still take the variation equal to 0, get the equilibrium conditions, which are the governing equation of governing differential equations, and then you will solve them using the method we saw in the last class, right? You will take the general solution of a differential equation of fourth order, and then you will substitute the boundary conditions to get a displacement profile like this.
Okay.
Right? We saw that in the last class, that we had a fourth order differential equation and we wrote a general solution for that differential equation. Right? And then when you solve for the constants in that general equation, you will find an equation like this. So instead, you can find constants using energy methods.
So if what's that called? If sigma equals E epsilon cube, how do you solve this?
So if sigma is E epsilon cube, the energy is no longer this expression, right? Now you cannot define H33 as EI, because EI, in that EI, I is integration over the area x2 dA, right? So this term will no longer be there because you will have different powers here. So you would have to take a step back, rederive this expression using the volumetric energy. So 1/2 sigma times epsilon d volume will give you another expression here, because you can no longer define H33. Yeah, go ahead.
Quick question. You had to use the abbreviation PSTPE, then assume the virtual work is 0. Is that connected? And what does that abbreviation mean?
So this is principle of stationary total potential energy.
Okay.
So that says that for a system to be in equilibrium, the total potential or variation or small changes in the total potential should be equal to 0 for any arbitrary displacements. So that's what it stands for. And the stationary total potential energy principle gives us the equilibrium condition, and the minimum total potential energy gives us the character of the equation, like whether it is stable or not. So that's very important to know. Yeah. Okay.